So our seventh question, let us see. So this is our seventh question. What does it tell? Let us look. We have a sequence of continuous functions from Rd to R, and which is given that m1 and m infinity, two positive real numbers, and any real number c satisfy the following condition. So Fn with L1 norm, the L1 norm and also given here, is finite, and L infinity norm also it is also finite. Basically L infinity is essential supremum, but here it is given only the supremum, that is also fine. And it is also given that the limit of Fn pointwise limit is c. We have to prove that the pointwise limit is 0. Okay. So here we will use Fetau's law. Look, there is lot of tempting attempts like using dominated convergence or uniform convergence to take the limit inside, but everything fails because we don't know we can dominate by a function or it is uniformly convergent or not. So these attempts are failed. You can try. So Fetau's lemma is the only thing that is give us relaxation and we can prove. Okay, now let us look what is Fetau's lemma. Now Fetau's lemma is, you can see Fetau's lemma, in measurable space, even any measurable space, let me change the color a little bit. Let's see this. Single color, okay, this one fine. This is measurable space where this is the main set, this is the sigma algebra on it, and this is the measure. So let any set x, the functions are defined from that set. Okay, so in a way, in our setting we have what we have. In our setting we have our full space Rd, then you can, let me write like that, our full space Rd, which is omega. Our sigma algebra is the Lebesgue measurable set, maybe we can write like that, and the Lebesgue measure, that's the new, and we take, we know this belongs to there, so our function is Fn from this to R, right? So this is important, our Fn's are from Rd to R, but we need 0 to infinity, so why not we take mod? If we take mod, this becomes 0 to infinity, right? 0 to plus infinity. Of course plus infinity, it can take plus infinity, but it will not take plus infinity because we know their supremum is finite, so this should be like that. But whatever, this is also fine. And define a function this, which is our constant function c, right? So we can take again the mods, that would be Rd to 0 to plus infinity again, because c is inside this. In fact our c is finite because supremum of them are finite, so c should be finite. So limit infimum, which is fx, is again a measurable function. Here we have a sequence of measurable functions. We need fn. Given it is continuous function, and you know continuous functions are measurable functions, right? So yeah, then this thing will happen. So we can simply use this result. In our case, this result will happen, and if I use this result, our question will be proved very easily. What is our f? Our f is c, because c is the limit of fn x, right? And as it is the limit, it is the limit infimum also. This is the limit infimum also. So in a way we can write as rd of c d mu is less than equal to limit infimum rd, mod. So we are taking mod, right? Because we have to take the mod, we have to work on the mod, right? So mod fn d mu, but that is less than equal to m1 given in the question, right? They all are less than equal to m1, so the limit infimum, in fact the limit will be less than equal to m1. But now this one is definitely infinite, but this is contradiction, right? That is contradiction. So this is the proof, and in fact in this proof what is important to see, actually we don't see anything to use m infinity here, right? Actually one thing that we can show, if c is not 0, right? If c is 0, that is 0. If c is not 0, then that is surely infinity. So if c is not equal to 0, but if c is 0, then there is no problem. n greater than or equal to 0 is fine. So c should be 0 in this case. But we don't use the fact that m is infinity. You can use the fact m is infinity to claim that c is a real number. C cannot be infinity. Okay. So that's a thing. So that's it. This is the proof.